Yeah, so I guess what we can do now is, and actually it's a good time because I think the first talk of the session is Bill Matthews, who, if you raise your hand, Bill, we can, I think, allow you to share. I think I might have gotten your slides, but I don't know if I've gotten them soon enough for now, so you can share. We can have a 10-minute Shine style presentation here. Oh, you got to unmute also.
Raise my hand, and I should.
Kelvin, can you allow him to share? Well, you can try to share.
Bill is a co-host, so Bill, you are able to share.
Okay.
Just find the button at the bottom of the dashboard.
Yep, I know. Okay, are you seeing my screen now?
Yes.
And I know, yeah, okay, it's sort of okay there. So I wanted to talk some about sort of picking up on Rohit's talk and just extrapolating on some of the things, especially some of the physics things that might be seen. In any case, the Alphane zone is an interesting neighborhood, whether it's a surface or a zone or a region filled with islands. So I just thought I'd start by sort of showing this sequence again, the sort of canonical, historically significant picture of a smooth Alphane surface with a feature around the current sheet. By the way, can you hear me okay? People hear me okay?
Loud and clear.
Yes.
Okay, yeah. And then moving to sort of irregular Alphane zone caused by variations in the source surfaces, and you see this in simulations by using magnetograms in the global simulations, and this is from a Cohen paper. And then finally, one of the frames that Rohit showed of this kind of inner boundary of an outer region where you sort of see the first crossings into subalphanic flow, and then an inner boundary where you see the first one moving outward of superalphanic flow, and then in between the possibility of these patches of transitioning from sub to superalphanic. Again, this was done with a Gaussian realization of the turbulence amplitude as interpreted from the Breach et al. Style turbulence transport model, which is used by a lot of the modelers. And I think this is kind of a creative way to employ that turbulence amplitude that's computed, then, which is this was Rohit's idea. Really, it's a good idea. And I just wanted to remind people that there's already lots of observational data that shows the presence of fluctuations apart from using these transport models. I mean, here's Craig's famous green plot. I call this the green plot. Other people call it something else. But this goes out to 15 solar radii. And as Rohit pointed out, the existence of these green blobs, and I don't know quite how to interpret what the fractional density contrast is, but Craig does magic with these things. And but in one way or the other, they definitely seem to imply not only variations in speeds along neighboring spokes, but also variations of density along them, with interesting levels of correlation in both the radial direction and the perpendicular direction. And I refer to Craig's paper for the numbers on that. But there's also the striation flocculation transition from the stereo imaging, also due to Craig's magic wand. And in this case, one can clearly see that there's some kind of isotropization happening here, almost certainly outside, mostly outside of where we think the Alphane zone would be. I think if it's at 12 or something like that, then it's in the green picture. And if it's at out to 27 sometimes, as Latova suggested from scintillation measurements, then it's also in this picture. So it kind of, and there's a gap between the two, I think. So, and in any case, PUNCH is going to have I think something like an order of magnitude better spatial resolution than these striation flocculation transition pictures, which very well could indicate, for example, changes in the nature of the turbulent fluctuations when you do have these transitions from sub to superalphanic. And let me just go on here. So one of the things that can happen when you're outside the alphane critical zone is that somewhere between the alphane critical zone and the first beta equals 1 surfaces, which are equally or maybe even more so vaguely defined, because beta varies quite a bit from stream tube to stream tube. In this region between alphane critical zone and beta surfaces, you can get shear instabilities, which can be triggered by tapping into the flow differentials that we saw in the green picture. And the green picture suggests 100 to 200 kilometer per second contrasts between different flow tubes are possible. Of course, there's also fluctuations in these flux tubes that are carried out, including, by the way, fluctuations associated with interchange reconnection, which would be an excellent way to trigger these shear instabilities once the energetics are favorable. And the energetics are favorable basically when the contrast in flow speed exceeds the local alphane speed, which does happen sporadically, even going back to the first orbit of PSP. And I think it's still happening. I haven't analyzed all of the data, but from plots that I've seen, it looks like it's typically occurring fairly frequently in the PSP data. Now, one of the things that can happen near the alphane critical zone, which I've sort of suggested here, is that underneath the zone or the surface or whatever it is, there's two characteristics for alphanic type fluctuations: an outward and an inward polarization, depending on the correlation of velocity and magnetic field. But an outward, after you pass the alphane critical surface, we know observationally that most of the alphanic type waves are outward propagating. And in fact, at the surface, the inward wave, of course, stagnates by definition. Now, different people's models and different people's interpretations of this stagnation phenomenon vary quite a bit. My own viewpoint is that I think that the amplitude of the inward fluctuation at the critical surface, if there is such a surface, is indeterminate. You basically have the possibility that the inward type fluctuations just stagnate and sit there, build up to some quasi-steady state, and act as a stationary target for the outward waves. And if that's the case, then the alphane critical surface or zone could very well be a site of enhanced turbulence. And also, of course, this shear layer instability, we had a paper last year, Ruffalo et al., arguing that this is one of the sources of switchbacks. And I want to remind people also that this is from an Usmanov-Chibber simulation published, I think, in 2018 in one of Rohit's papers. But the range of scales where you expect to see alphane critical transitions happens also to be the range in which the global simulations indicate that there's a peak in the amplitude of the energy per unit mass of the turbulence. So it's pretty easy to imagine that since that's sort of going to happen anyway, independent of whether there's reconnections or roll-ups or anything else, that these large amplitude fluctuations should be able to trigger all kinds of dynamics. And there's even some papers recently suggesting that the switchbacks themselves are simply caused by the fact that you have sufficiently large amplitude fluctuations to sometimes turn around the overall magnetic field. And also these could trigger buildup of turbulent heating near the critical zone, and also enhanced heating throughout this region, and so on.
About a minute left, Bill.
What's that?
About a minute left.
About a minute? Yeah, that's good. So another interesting feature, and this is from recent work done by Manuel Cuesta and Rohit Chibber, averaging over 5 Parker orbits, is that if you look at the proton density and its standard deviation, and also delta rho over rho, here's delta rho over rho at the bottom. You see that as you move in, and these are the averages and standard deviations about the averages from 5 Parker orbits. You see that there's a suggestion that inside of 50 or 70 solar radii, that the fractional density fluctuations actually start to go up. Now, whether they continue to go up and maybe peak near the Alfvén critical zone would be very interesting. If they do, that may be good news for PUNCH, because we, at least from a theorist point of view, it seems like having stronger density fluctuations might give a better signal to noise ratio. So just to summarize, if you have near these different sorts of Alfvén critical regions, you can have stagnations of the inward fluctuations. If it's a complex transition, like these islands, fractal islands that Rohit was suggesting, then this is happening at multiple locations. Now that's really an interesting idea, because that would mean that you have enhanced turbulence level because of this stationary target business. You have enhanced reflections because there's going to be lots of Alfvén speed gradients inside this region. You could have therefore enhanced acceleration of the wind because you have increased ponderomotive force because you have more turbulence. It looks like there could be higher density fluctuations because there's more turbulence. And again, the Parker observations are hinting towards that. You would also then have more heating because there's more dissipation, more particle energization because there's more turbulent EMF and more trapping, and also more scattering of solar energetic particles. Another interesting angle on this, and the red things here are the things that I think that PUNCH can definitely tell us something about. There's also this background problem of the problem of length scales in solar wind turbulence. We've known for a while, since the Ruiz paper in 2012, with some more recent papers confirming that when you measure correlation lengths parallel to the mean magnetic field moving towards the inner heliosphere, there's a different radial variation of the parallel correlation lengths as opposed to the perp correlation scales. They become almost equal at 1 AU, but close to the sun, not. And what causes this? Does it come from simply, does it come from the Alfvén zone or Kelvin-Helmholtz roll-ups that induce a shorter perpendicular scale by injecting energy in some kind of region, like one of these three? Or does the Alfvén zone act like a wind tunnel grid? If so, if it enhances turbulence, is PUNCH going to see this? Of course, it might also be that we're simply, that there's a selection effect just caused by the fact that you see more radial field when you move closer to the sun. But that begs the question as to why the parallel scale is as short as it is. Does that go back to some kind of dynamics near the Alfvén zone? We simply don't know the answer to these questions, but I think PUNCH can address a lot of these issues. So I'll stop, and I know I went over, Steve, I apologize.
That's all right. So yeah, so please, everyone, put your questions into Slido, and we will get back to them and have discussions there too. The second Shine style presentation is Thanasis Katsianis. Are you there?
Yes, I am. Can you hear me?
Yes, yes. Please share your. Actually, you know what? I think I have your slides.
Yes, if you could share them for me.
Sure,
sure. I had problems before. I don't want this to happen again.
There we go.
Okay, right. Can we go directly to the next slide? Because I'm trying to keep it short. So yes, so let me talk about the DIN model that I've been working for a while now. And basically, it's a numerical model that is based on the assumption that temperature, electron density, gravity, and the solar wind balance out. So the principal idea, you can see this in this moment equation where the whole model is built around, is that any imbalance between the temperature, the density, and the gravity becomes the solar wind. And here, of course, we are talking about the ambient solar wind under quite some conditions. So we try to keep it simple. So basically, the whole idea of the dynamics between density and temperature has been around for years. There's been a few models and a few papers. There's been a model by Parker and a paper and a few papers by, for example, Potas, Brandt, and Gibson more recently that use this hydrodynamical idea. But they all assume that at infinity you will have a temperature of 0 and pressure of 0, which you know it's not true. But the previous models could not cope with different values very well. So by adding this last term in the moment equation, we can compensate for that a bit. And then we have the Lemaire and Stegen paper of 2016, where they used density fit by Saito, which was made in 1970, and they add another term to allow for measurements that are taken at 1 AU to correct for a better density and include the density and the velocity of the solar wind at 1 AU. And here in the graph, you can see that the various densities as they are produced by the various models. So the black line is the polar region as introduced by Saito. The blue line is the equator region. Now in this slide, sorry.
Sorry about that.
Yeah, no problem at all. And the red dashed line is the polar region without an outflow. So what Lemaire did is he introduced in the black line, you can see he increased the prices of the density for values larger than 3 solar AD, just to compensate for the largest values we can measure at 1 AU. Next slide, please. And in the next slide, we can see the temperature distributions as they come from this model. So as you can see, the left graph is for the equator. Now we use the equator as a proxy of the slow solar wind, and we use the polar region as a proxy for the fast solar wind. So as you can see, depending on the value of the solar wind velocity at 1 AU, we can get different temperature distributions, even as low down as 0.1 or 0.2 solar AD of solar altitude. And you can see a similar picture for the polar temperatures on the right-hand side graph, where for values say about half solar AD of solar altitude, the temperature differs based on how much velocity you measure at 1 AU. So what these graphs basically mean is that there is a big difference in the temperature distribution. You can see very low down, even at 2 or 3 solar AD, based on depending on the measurements of the solar wind of velocity and temperature and density, sorry, you get at 1 AU. So it clearly shows some connection between those two things, and that has implication on the energy. So it just shows that if there is some heat, it's likely to be some heating in this region that affects the propagation of the solar wind later on. Can I have the next slide, please? And now let's see what is the relation of this work with the PUNCH mission. So in a way, the DIN model is going to be an end user of the PUNCH data, in the sense that the PUNCH mission will measure solar wind speeds at low radial distances, which is something we need, because it's for the moment you're using the speeds measured at 1 AU as approximation. It will be very good news for us if the PUNCH mission can provide us with measurements directly in this area. Also, the large-scale flows that the PUNCH mission is going to measure is going to be important for us, because for the moment we are only using eclipse observations of the ambient solar wind out of a necessity, and those observations spread over years, so we cannot have any dynamical, we cannot, any dynamical information on how this model can work for a shorter time scale. And of course, it's a B model, the DIN is a B model because it uses as a proxy the equator and the polar density distributions. It will be much better if we have more information from PUNCH rather than making this approximation. And that's all I have for the moment. Thank you.
Great, thank you. Yeah, no, this looks like a nice tool for taking, the PUNCH constraints on both density and velocity and trying to use some extra physics constraints to get information about the mean temperature in the corona. That's great.
Yeah, the limitation we have for the moment is exactly this, that we don't have measurements for the area we're interested on. We have measurements at 1 AU, and of course, there are a lot of things that are going on, between the 10 solar AD and the 200 solar AD. So this is what we need right now.
Great. So yes, so everybody, please put questions in Slido, and we can continue the discussion there. Let's have one more Shine style discussion. Is Luis Vieira there?
Yes, I'm here.
Okay. Yeah, so I've got the slides up, and I can step through them if you like. Sure. That's this. I just added this to have your name here, and the next one is your first slide.
Yes.
So yeah, please. Yeah.
So first of all, Stephen and colleagues, thank you very much for the opportunity to talk a little bit about our initiative that I'm sure it's overlaps with the PUNCH mission. So first of all, let me talk a little bit how it started. As you may know, INPE has research activities in several fields, including meteorology, weather forecast, climate research, Earth remote sensing, engineering, and so on. And of course, one important for us is the engineering. And what happened is that when I come back to Brazil, INPE was already starting to move to update the research activities, including initiatives as our space weather program that it's running now. So what we realize is that if we'd like to really progress in heliophysics, we need to have also our contribution in the instrumentation part. It's not, we really have to contribute somehow to the international community. And so at that point, we start to study and to figure out how we could contribute in that way. We took some funding opportunity and we proposed to build a proof of concept spectropolarimeter. So that was our base to progress in that direction. Later on, we had the opportunity to realize a feasibility study for a solar observing mission that we call Galileo Solar Space Telescope. At that point, we proposed to have 3 scientific objectives. The first of all, understanding the evolution of the magnetic structure of from the surface to the outer layers of the sun, connecting this to the evolution of the solar total and spectral irradiance, which affects the Earth's climate, is a central point of interest of our institute also. And as we come from magnetosphere physics, also to address some basic understanding on the influence of the sun's activity on the geospace. So as I mentioned, we have as the main purpose imaging the sun, employing our remote sensing capabilities that we have already developed at the INPE with several Earth remote sensing satellites. And from this understanding that we are able to do this kind of observations, we propose so to build high resolution images to sample the sun in the visible and ultraviolet. So we have some basic assumptions that you may go for the next click. So we have some concept that we sell to our funding agents, and basically what we say is that it's quite important to the international community, solar physics and stellar physics, to have this kind of accurate measurements of the solar magnetic field. It's also important for us to develop critical technologies that may be incorporated to our industry. And of course, it's very challenging for us, and we may really, in the end, be part of this international effort to understand how the sun works. And of course, that is one point to why I'm presenting here is that we are very interested to gain know-how by collaborating with foreign colleagues and groups, and also eventually, as the project advances, we may have some contribution from hardware groups. So the next one, please. So basically what we did up to now is we realized a feasibility study in which we, based on the scientific objectives and the requirements that we proposed, we discussed with our engineer teams, and so we come out with some very raw idea of what we can do with the research that we have available now, I think. So on the right side, you can see the concept for the imaging payload. We proposed 3 telescopes, one for high resolution imaging in the visible and ultraviolet, and 2 others for full disk observations, all of them with spectropolarimetric capabilities. Now you see the concept of our high resolution telescope on the bottom, and a little bit up the full disk imager. On the left bottom, we can see our initial concept for the high resolution telescope, 500 millimeter telescope. You can see so the optical paths for the ultraviolet in blue, the red channel in the visible, and also some tracking camera for corrections of the imaging. We studied 2 possibilities, one geostationary orbit and a low Earth orbit. We can see on the upper left panel, in which we have the 2 solutions that come out from this study. Of course, that things changed a lot since the beginning of the spread of the coronavirus, and the funding in Brazil reduced drastically for science, and also not just for science, but for everything. And we collapsed now for a lower orbit solution. So based on the success of the deployment of the Amazonia 1 satellite, Earth remote sensing satellite, we decided to evaluate the feasibility to employ this service model from this mission, which is a multi-mission platform, as a solution for our space platform. So we are working in this right now, and in the next step, as we conclude this phase, to show that it's feasible to employ this platform to solar observations, we can move on and proceed as a review of the scientific goals that, of course, we hope our international community can contribute also. So thank you very much, and we are very open to suggestions from your side.
Great, thank you very much. So again, let's have some more questions in Slido about how this future mission might be able to work with PUNCH and other heliophysics missions too. So yeah, so let me hand it over to Kurt for the remaining Shine style presentations.
All right. So the next presentation that is up is from Belvir Rathor. I hope I'm not mangling your name all too badly. So Belvir Veered there. There you are. All right. So if you can get unmuted.
Belvir, you are a co-host. You are able to unmute.
Okay. There you go. So, okay, I'll start. Yeah, we can hear you. So I'll start sharing the screen.
Please show me.
Maybe. All right. So can you see?
Yeah, I can see, but I have changed my presentation to yesterday.
Okay. So if you want to share from, or if you want to go from your screen, that's fine.
So may I show from my screen?
Or is that not possible? Because I just downloaded this. I guess I downloaded it yesterday.
Belvir, I have a copy of your presentation as well. It looks a little different than what we see here, so I can share this one.
Yeah, this is okay. Okay, so may I start?
Yeah, go ahead.
Okay, so myself, Belvir Rathor. I'm from Government College, Nationalganj, Sihor, India. So next, please. So here today I present the impact of solar wind on the geomagnetic storms. So as we know that the change and the disturbance in the magnetic field of the Earth, that is known as the space weather, and that space weather is due to the impact of the solar wind and the interplanetary magnetic field. So for this purpose, we have collected data from the OmniWave website site, and we take all the solar wind parameters and interplanetary magnetic field parameters along with geometric indices like KP, AP, and DST. So here we used a critical value of DST, and we find some statistical relation between the solar wind parameter and geomagnetic indices. So in this table, we have shown the different parameters which are taken from the OmniWave website, which that data is collected from the different satellite which is situated at the one astronomical unit. So next, please. Next slide, please. So here we done some statistical study. So we find a relation, correlation between the interplanetary magnetic field and the DST. So first we take with, in the first figure, we have take total magnetic field versus DST. So we found a linear relationship between the DST and the total magnetic field. So as well as we have also taken the Z component of the magnetic field, density, temperature, speed, and pressure. So here we found that we have found a linear relation between the total magnetic field and the southward component of magnetic field and the speed are the more linear, and we have found a very good correlation between that parameter and the geomagnetic parameter. So we can conclude that the total magnetic field and the southward turning of the magnetic field is more responsible for the intense and the moderate geomagnetic storms. So further, we can develop some model by using this linear relationship for the space weather prediction purpose. So here I will stop here. Thank you.
All right, thank you. If there's anybody has any comments or questions that they have based on this presentation, remember to enter them into Slido. So that brings us to the end of the presentations that we have for this first session, this first Shine type session. So are there any questions related to the past four presentations that we have seen? Otherwise, we'll go back to questions that were entered into Slido earlier today.
And just a reminder, just raise your hand so that we are able to unmute you and we can see you rise up to the top on the list.
All right, Craig, go ahead.
I've got Alphane surface on the brain here now. I want to go back to Bill and Rohit, if I may, and ask about these islands of Alphane speed variation along the radial streams. Seems to me that's quite different than what we saw in that 18 paper, right? Where we said that the striations, the variation across the striations was enough to induce a zone, provided that you're considering low enough K values, right? Long enough wavelengths of Alphane waves. But this is a different mechanism entirely that it seems would produce zone-like dynamics. I just wanted to expand, or to hear you guys expand on that a little more.
Is it really different, Craig? I mean, your green movie indicates that you have radial variations, right? And the existence of the different stream tubes indicates that there's some kind of angular modulation as well. And if you convolve those two, you have variations in all directions, which means that sometimes it should be above and sometimes below. I think the characteristic feature of what Rohit did for these beautiful pictures that he showed is he used the Gaussian random number realization, which is itself an idealization and may not be entirely accurate, but it's someplace to start, right?
Right. Okay. Yeah, it makes sense. I think you're right that the green and purple movie there sort of underestimates the effect of these variations in the radial direction, right? They're all smeared by temporal variation in the processing. So the fact that they're all, a solar radius wide is an artifact, right? There's probably structure going much smaller.
Maybe Rohit has something to add to that.
I mean, the study that we did, it's sort of constrained by the resolution of the code that we're using. If you have a finer or a coarser resolution, you'll get blobs at those scales. It's really constrained by the grid size, which happens to be a few correlation lengths. Okay. And the other thing I would say is that right now we are using a Gaussian distribution. So these are, the fluctuations are separated by a few correlation lengths, so they are not supposed to be correlated. But you can still, instead of using a Gaussian distribution, you can use a distribution which produces more clustering rather than sort of the homogeneous islands that we see. So like, just a more intermittent or patchy with larger islands and smaller islands and so on. You can also produce fluctuations that have a desired like spectral distribution. So all those are refinements to this synthetic fluctuation approach that in the future we would like to continue working on.
Sure. I understand there may be some data that we can't discuss yet, but hopefully the embargo will be lifted by our next meeting.
That'll be awesome.
Craig, one of the strange features and just coincidences about simulations like the Usmanov simulations that Rohit is using is that the spatial resolution in the area where we're looking, say 30 solar radii or something like that, is about comparable to the spatial resolution of the stereo imaging that we used.
Oh.
So for totally different reasons, and the errors are totally different, and there's no Thomson plateau and so forth. But as PUNCH comes around, we also should have higher resolution codes. I think one of your team members already has a higher resolution code that we've seen on the team discussions. That I can't remember the young woman's name who has that code, but that's really somewhat higher resolution than our codes. But PUNCH and the simulations will evolve together to higher resolution.
Thanks,
Yeah, I
Phil.
would just say that you do need, like even with the higher resolution codes, you can't resolve inertial range fluctuations. So you still need a turbulence model, subgrid turbulence model with the higher resolution global solar wind model to be able to produce some kind of estimate of turbulent variability. Just want to say.
Thanks.
Yeah, so is there any more comments on this topic? Otherwise, we'll move on to questions from Slido, which relate to CIRs. So any more questions or comments on Alphane surfaces? Remember, raise your hand and then you'll be moved to the top and Kelvin can unmute you. Sarah, go ahead.
I actually just put a question in the Slido for Thanasis, which was, he's talking about how PUNCH is going to provide some important data in that gap in between what we can observe closer to the sun and then 1AU. And we are on the hook for providing flows at certain heights and certain times of day, but we're hoping to do much more. And so I was wondering what the ideal model constraint of a flow map would look like to him.
Well, it's a bit difficult to answer this right now because I want to see the data first. In the sense that this model works well so far on very large scales, both spatial, of course, scales, but also temporal scales. So we are looking at a very large, we are looking at a stable condition where we don't have any variation. This is how it works now. So what I want to do is use the PUNCH data to shorten the scales, especially the temporal scale. So what I want to do is to see how well it will work on the variability you get. How I can adapt the model to compensate for that, So I will start with maybe synoptic observations, and then I will try to move from there. So I can't really say for the moment, but the shorter the time scales become, the better it is. It means the better we understand the outflows on the corona and the temperature, of course. That's another thing.
Okay, is there any other questions on the presentations that we just heard, whether it's from Thanasis or from Belvier, or of course, still going back to Bill? Okay, if there are no other questions, then we will go on to Slido questions related to CIRs. And I guess that means, Vic, if you're available to start answering some questions. The first question is from Pradeep, who is completely new to CIRs and asks a really good question. How different are individual CIRs?
Well, I think we answered someone's slide a bit already, but they can be quite different. And the pictures I showed, for example, were really, I guess what you'd call idealizations and all. They probably aren't that regular. and they are most regular during the low point of the solar cycle. By the time you get over to the active point of the solar cycle, they're probably much more time dependent in the sense that they exist for a shorter period. They are not a lot less regular looking, and they could tend to come and go. So there's no one kind of CIR, I guess, that you could focus on. It's more the general phenomenon, and those were intended to be kind of idealizations of it that I showed.
Okay, I mean, I see, Craig, that you have an answer in the Slido. If you want to, do you want to elaborate more on what you wrote under Pradeep's question?
Sure. Just from the very few imaging studies that we have, CIRs aren't even the same as themselves. Which is to say, the ones in the Woods paper, the ones I've analyzed and not published, I'll show one a little later in the afternoon. They don't look very much like the smooth shell models that are drawn in the cartoons. They're much more irregular. And so there may be a large envelope that looks that way, at least in the ones I've looked at. Vic's looked at a lot more data than I have. But I would be shocked if it turned out that CIRs are entirely uniform.
Mm-hmm.
Yeah, I would expect to see a lot of variation if you could, the more imaging you get. And, I just don't think, like I said, those schematics are idealizations, and you have to realize that that's not reality there.
No, that's certainly true. What we've seen with CMEs, imaging of CMEs as well, that they never look the way, they never look nice and smooth in reality as we make them out to be in the models with all the idealizations we put in. So I think it's safe to assume we'll have the similar surprises with CIRs.
Yeah, and you have to remember too, they're interacting with the background as they go, which that can be quite significant. There are places where the fronts can move around a little bit because the background conditions are less constraining, and other places where they can move around a bit because they are, in some sense, you can think of them as kind of a wave. They're not hard structures, let's put it that way. Same way as CMEs.
Right. Pradeep, do you want to make any comments about what you've heard so far? Follow-up questions?
Yes, thank you for discussing. Now, of course, I'm very new to this CIR topic. Now, if we talk about CMEs, then we know that these are some rigid structures that propagate outward and then they kind of decay or interact with the background. But the CIRs are unusual in that they are transiently forming because of two features interacting with from the solar in the solar wind. Now the question is what are the time scales associated with the CIRs and how long do they live? Are they transient? Can we associate a particular length scale to a CIR? All these questions, of course, I do not have answers, and hopefully Punch will be able to provide, let's say, new insights into this area.
I would say, well, it depends when you ask the question, so to speak. CIRs can reappear rotation, rotation, rotation in some solar cycles. In certain times of solar cycles, they can reappear like that 3, 4, 5 times. And then other times you see them once and they kind of disappear. And during solar max, if you see the same CR coming around the second time, it's kind of, I wouldn't exactly say unusual, but it's you don't count on it anymore happening because the whole corona is evolving so rapidly. And they are creatures of how the coronal holes are evolving, and that's in that rate that just changes at various times, and in fact from cycle to cycle. If you go back into the 70s, for example, the CIRs at those times, especially in the lower part of the solar cycle back then, they were very regular. You couldn't quite set your clock, your watch on them, but they were pretty regular. In other solar cycles, they haven't been so regular, even in solar minimum.
Heather, do you want to make some more comments about in response to these to this discussion? I think, Kelvin, you need to unmute Heather.
Yeah. Okay. Yeah, there's a lot known from the in situ observations, and as Vic had alluded to, the CIR that you see, it's a compression region, and so it depends on the properties of the wind coming out of the fast wind coming out of the coronal hole, and also the wind in which it propagates into. And so it's going to be propagating into a slow wind region that was emitted at the same longitude earlier than it. And so it develops en route. And I know some other people had mentioned that, you know, you don't necessarily see them really down low in the corona because they haven't formed yet. So there's truth in that as the fast wind runs into the slow wind ahead of it, it develops more and more, and it gives a compression signal. So the larger the difference in the speed, the more it's going to develop, and have an increased pressure, density, temperature. So as it goes along, you get this whole compression squishing effect, and the field strength goes up as well, because you push the field lines closer together. So it's a whole evolution, and it depends on the property of the slow wind ahead of it and the properties of the fast wind. So the really large coronal holes, and at equatorial latitudes, the really largest holes are going to be polar coronal hole extensions. They can produce wind up to about 830 kilometers per second, but the smaller, more typical, more isolated equatorial coronal holes may only produce a wind speed of 500. So if you say the background wind is about 400, that's only a difference of 100 for a small one, but it's several hundred difference in speed for a large coronal hole. So for these large coronal holes, you're going to have a more well-developed CIR by the time you get to 1 a.m.
All right, thank you. I know we're into our break time right now, but I don't want to break up this discussion that we're in at the moment. So Bill, if you have a question or a comment that's related to this topic,
yeah,
go ahead.
So actually, I had written a question for Vic onto the Slido, but I think it got lost in some other thread. So I have a question, and it relates to a comment. The comment part is that the CIRs, the way they develop canonically, actually start off being shear layers, and as they move out further, they sort of convert from being shear layers into compression layers. But there's always shear present until you get maybe to 100 AU or something like that. But the question that I had placed for Vic was, and also this is a punch question in general, is that have people studied shear dynamics along the flanks of the CIRs in addition to the compression part of the physics? Has that been done, and will Punch be able to analyze that?
Well, as I mentioned, I mean, that shear business has been understood, you know, back to, like, say, from Helios days. That's when it was kind of highlighted. People didn't pay much attention to that before that. Mm-hmm. And then it became obvious. But there's been actually a lot of, particularly people looking at energetic particle propagation and stuff within the CIR itself. And you know, there's a number of papers to do with those shear flows. You're right. It starts out as a very much a shear layer really near the sun, and gradually, because of the rotation and assuming that the overall structure is somewhat quasi steady, that turns it along with the spiral angle farther and farther away from being a radial.
Did we just lose Vic?
Yeah, I think Vic, we just lost somehow we lost you.
Maybe that's a
I was going to say.
forces of nature.
Later,
Time for a break.
Okay. Thanks, Vic. We'll catch up with you later.
Yeah. Yeah, so we'll take a break right now. We've got a 10-minute break scheduled, and we will do the entire 10 minutes. And then so we will reconvene at some hour plus 46 minutes, depending on what time zone you happen to be in. So we'll see you then.
See y'all in 10.